Hi, chemistry students. I want to go through today the rules that govern the identifying factors and where we find those electrons. So where do we find those electrons? And you've kind of been doing that already because you kind of said, oh, we have these, 1s orbital and the 2s orbital and so on. But there's definitely rules that kind of govern this. You've already been doing this, so this is sort of just the kind of the paperwork that goes along with it, if you will. By the way, I'm sitting in my back office. I don't have a room right now, so so the three rules that govern where we find those electrons. The first one, the Aufbau principle, states that electrons occupy orbitals of lowest energy first. So when we started writing these electron configurations, we said, oh, as we move through the periodic table, we always fill the 1s orbital first. When that's full, then we move to the 2s orbital. When that's full, the next one in line is the 2p orbital. And of course, it follows the periodic table. This is a bit messy. It follows the periodic table, so remember I'm writing with my mouse here. This is the 1s. And then we go 2s, 3s, and 4n. But we go from the 1s. Remember, helium kind of fits over here too. So helium kind of fits over here. So 1s. And then when that's full, we go 2s, starting right here, 2s, and then we follow straight across, and the next one that fills is 2p. We split that into px, py, and pz. Each of those orbitals has to have one electron before any has a second electron, and so on. So we go 2p, 3s, 3p, 4s, then we go 3d. We said this is the d sublevel. And it starts with a 3. So we really go 4s, 3d, and so on. So those are in order of energy levels. There is a visual in your book. Some people like to use this. I actually don't like it as much as just using the periodic table because these feel right in order that you find them on the periodic table. But it does say the first energy level is the 1s. And then we go 2s. Then we go 2p, 3s, then we go 3p, 4s, but then we go 3d, okay? So each of these are in order of energy level. Some teachers teach the method of using this. I remember learning this in college, and honestly, for me, it didn't make as much sense as teaching it because I could just use the periodic table, and that also shows that periodicity and why the periodic table is arranged the way it is. So anyway, Aufbau, very simple. We start with 1s. Then we go 2s, right? So there's an order they fill by order of energy. The next one is called the Pauli exclusion principle. An atomic orbital may describe at most 2 electrons. So an atomic orbital is, like the 1s is an atomic orbital, so is the 2s. The 2px is one atomic orbital. The 2py is another atomic orbital. The 2pz is another atomic orbital. They can only have 2 electrons. If 2 electrons are in fact in these orbitals, they're spinning in opposite directions. One spins this way, one spins this way. And we really say one spins clockwise, one spins counterclockwise. So Pauli exclusion is they can only they can only have 2 in an orbital, and if there are 2, they're spinning in the opposite direction. Hund's rule: every orbital in a sublevel is singly occupied with 1 electron before any one orbital is doubly occupied. And again, you've already done this too, hopefully, on your electron configuration lab. So if we look at something like nitrogen, and we've already done examples of this. So nitrogen has 7 electrons. First we fill the first energy level, right? So the 1. Then we fill the second energy level, which is 2s, and then 2p. But we have to break that 2p sublevel into 2px, 2py, and 2pz, those separate orbitals. And each of these has to have 1 electron, represented by the arrows. So 2px, I put 1 electron here, 1 electron in the 2py, 1 electron in the 2pz, and because this is 2p4, I can then go back, only after each of these has 1, I can go back and add a second electron. So Hund's rule, each dog wants their own house. That's what I think, like Hound's rule. They each want their own house, nobody wants to share. We only share if every house has someone in it. That's one way to remember it. And I hope you're finding, if you're looking through these notes, I have lots of examples in here that we didn't go over in class necessarily. I don't have access to my board right now, so it's really hard for me to write anything. But and then the next thing I wanted to talk about, quantum mechanical model. Each electron has 4 quantum numbers. This is our quantum mechanical number. Sounds like kind of big word, but this is what you've been doing this whole chapter. So the 4 quantum numbers are simply the 4 identifiers. All right. So the first, let me pick a number, or Bo likes olive green. Let's use that. The first quantum number is the energy level. Energy level is this, the 1 in front of the S, the 2, so this is the second energy level, and I know it asked you about that in the lab sheet as well. And then, so that's the first quantum mechanical number. The first quantum number or identifier is what energy level do we find that electron in. The second one is what's the shape of the orbital. Is it a P or a S, P, D, or F shaped orbital? So that's the second identifier. The third is the orientation of that orbital. Is it a 2px, a 2py, or 2pz? What plane am I finding that orbital on? So the orientation of that orbital or suborbital. So that's the third quantum identifier. And then the fourth one is spin direction. If there's 2 electrons in this 1s orbital, which direction is the electron spinning? It's either spinning clockwise or counterclockwise. And the big rule here, no 2 electrons can have the same 4 quantum numbers or quantum identifiers. That's really important. So I think quantum mechanical model sounds more complex than it is. It's what you've been doing already, so I think you're already pros at it. And then just really quickly, how are the quantum mechanical model and the Bohr model alike, and how are they different? So they're alike, and it actually addresses this in your book. That's kind of why I'm bringing it up, and I think it asks on one of your worksheets. So how are the quantum mechanical model and the Bohr model alike, and how are they different? They are like the Bohr model. So remember, this is the Bohr model, the concentric rings, the electrons are orbiting almost like how planets orbit the sun, and so on. And the quantum mechanical model is this whole, there's different shapes of orbitals and sublevels and so forth. So they are the same in that the quantum mechanical model restricts the energy of electrons to certain values and certain areas. So there's lower and higher energy levels, if you will. They're unlike them in that the paths, we know that this path thing that the Bohr model does, even though it's super easy to draw that, not super accurate. Because really we say the exact path of the electrons is not necessarily known, but we think of it as more of a cloud. So I will find electrons anywhere in here or anywhere in here, the 2 electrons that occupy this 2px orbital. I'm more likely to find them in these areas of the cloud that are larger. I'm less likely to find them in these little areas that are smaller. So that's how it's unlike the Bohr model. We think of it as more of an electron cloud, if you will. So this information should be sufficient for you to hopefully complete the lab if you haven't already. This just sort of, I think, solidifies some of those questions. And then we can do the first couple worksheets that go with this chapter.